Hello everyone, I'm Srijan Das from UNC Charlotte. Today I will be presenting AAN, Attributes Aware Network for Temporal Action Detection. This is a work done by Ray Dai at INRIA in collaboration with UNC Charlotte and Stony Brook University. So in this work, we will talk about temporal action detection, which is one of the most fundamental and important tasks in video analysis. This task aims to detect the action occurrences along time in untrimmed videos. So on the left-hand side, you can see that temporal action detection not only detects the occurrence of an action, but it also classifies what type of action is it. There are many real-world applications related to this task, such as human-robot interaction, human store, autonomous car, sport action assessment, and many more. So most previous work focuses on detecting actions in sparsely annotated web videos. These datasets always have few action instances in a video with simple temporal relation. Here, the actions are well defined by the background and the actors are always in the center of the frame. So as the ultimate goal of action detection system is to deploy them in a real-world scenario. How about the real-world scenarios? There are different challenges involved in real-world videos. In spatial domain, there are so many fine-grained scene details. Let's say there are so many objects in the scene and how the human interacts with these different objects in the scene. The human-object interactions needs to be modeled by the system. And in the temporal domain, it has challenges such as long duration videos, composite activities like cooking, and there can be occurrences of concurrent actions. So we try to take a step towards action detection in this complex real-world setting. So this is a classical action detection framework where the untrimmed video is fed to a visual encoder, and then there are temporal features which are fed to a temporal model in the second step. And this temporal model has a detection head, which gives you the actions per frame or per segment. Firstly, we have this visual encoder, which maps the video from the raw pixels to temporal features. So the features are extracted by a visual encoder. This visual encoder is a convolutional-based or transformer-based model that maps the pixels into a series of features. A single temporal feature covers only a few frames. And this is the only step in the temporal action detection which handles the spatial domain of the videos. Because after this, the spatial resolution is preserved across the channels of the temporal feature. So by stacking the snippet-level temporal features along time axis, we can obtain a preliminary video representation. This video feature is of size t cross d, where t represents the temporal dimension and d is the channels. Then comes the temporal module, which is used for modeling the relations across the temporal features, which is a sequence-to-sequence learning process, and it projects the features from t cross d to the class prediction scores per snippet or per frame. So several works have been done in this direction. People have come up with different types of temporal models. One is based on proposals. It is very similar to object detectors, where you have different region proposals, of course, across time, which represents the different actions in the videos. But these are very exhaustive for long videos. Then there is a stream of work around temporal convolutions. So convolutions across the time axis is applied across the entire videos. It has been also varied with different types of kernels, like the Gaussian kernels in super event and TGM. And then there's a stream of work using temporal transformers or graph convolutional network, where the nodes are different objects present in the scene. So in this work, our objective is that, can we find the relevant nouns, objects present in the scene? If we can extract such information, the next question is how the object state changes in a video. Because if we are able to solve these tasks, then it will be a very crucial cue for the action detection system. But the question is, how do we incorporate such details in the action detection framework? So one naive solution can be just choose a visual encoder that can better represent the object semantics in the scene, isn't it? What will be the choice for this visual encoder then? Let's come to OpenAI's CNIP. Everyone knows about that. I will just reiterate it again. CNIP is a vision language model which has been trained on 400 million image text pairs with a contrastive pre-training strategy. And this learned text and image encoders can be used for several zero-shot computer vision tasks. And the representation learned and the image encoder can be also called as some kind of pseudo text. So can we use CNIP for temporal action detection? So we did some very preliminary work 2 years back on Ego 4D dataset. We actually fed the Ego 4D images to a CNIP model and asked questions like, where is this image taken? What are the verbs in this images? What are the nouns in this image? And what is the scenario? So we also fed several text queries like the places, verbs, nouns, scenarios pertaining to the scene or the distribution. And we realized that CNIP does pretty well in recognizing the nouns, the place, and the scenarios of the images. But it is extremely noisy in detecting the verbs, which makes sense because CNIP is never trained on videos and it cannot model the motion patterns. But it is important to note that it can help us to retrieve different information about the object semantics present in the scene. So how can we leverage CNIP features for fine-grained action detection? We can just replace the I3D visual encoder with a CNIP encoder. And this should be able to solve our task. We should be able to encode fine-grained object semantics into these temporal features, and it should be able to perform better. But this framework underperforms in contrast to visual encoders like I3D, which is trained on kinetics and the trimmed dataset. So that's why we came up with attributes-aware network. It is mainly composed of 3 components, where we have the frozen CNIP to extract the features. Then we have attribute extractor and graph reasoning block. So what is attribute extraction doing? We have a CNIP encoder which extracts the frame level features. But from these features, we want to get the different object semantics present in the scene. For example, if bag, book, sofa, these are present in the scene. So the attribute extractor should be able to disentangle this information from the unified representation we obtain from the CNIP feature. So the attribute extractor maps the video from a T cross D dimension to a T cross N cross D visual semantics. The visual semantics is supervised by the attribute representation in the training distribution. That means we take the CNIP features, feed it to the attribute extractor, which is nothing but just a linear layer, and it is supervised by the language semantics. So we provide text prompts or attributes which are associated with the activities of daily living. So they are basically the different nouns, places, scenarios, which are relevant to the training distribution. And to supervise this visual semantics that we learn from the CNIP features, we use a mean square error between the visual semantics and the language semantics. Then, after we obtain these attributes for each feature, we use a graph reasoning block to model the temporal information as well as model the attributes within the frames. So each frame is represented as a graph. Each attributes are the graph nodes. Edges are initialized based on the statistics of attribute occurrences in the training distribution, and these edges will be updated. So then graph reasoning block consists of multi-head attention, which learns the inter-attributes relations and updates the edges. It also consists of the graph convolution, which is performed on the learned edges. So basically, in the network, the relationship between the different attributes are learned. And then in order to model the temporal information across time, we use temporal convolutions. The total loss to train attributes-aware network is the convex combination of the mean square error between the language and the visual semantics, and the binary cross entropy to learn the multi-label classes. For experiments, we have used 2 complex temporal relation-based datasets, Charades and Toyota Smarthome Untrimmed. Both the datasets have very complex activities, and just a note that for Charades, we evaluate on its localization setting. In our application, we show the effectiveness of our proposed modules. So if we want to make use of CNIP for action detection, just straightforward replacing the visual encoder with CNIP doesn't work. We need both the attribute extractor and a graph reasoning block based network for modeling the temporal information and the attributes in the scene. Both of these components are crucial to get a very high action detection accuracy. We also aberrate the different components or our design choice of the graph reasoning block, and we see that both multi-head attention and temporal convolutions are required to get a very high accuracy. And finally, we also show that our attributes-aware network is very robust. It can be used with different type of features. It's not necessary to have only CNIP features. It works with I3D features as well. And you can also change the temporal model. You can use other models like MNPs or PDAN or MSTCT, which are state-of-the-art methods in this domain. We also see the state-of-the-art results on Charades and TSU. Clearly, attributes-aware network outperforms all the present state-of-the-art methods. One of the reasons is that we are using a CNIP model, whereas all the other state-of-the-art methods have been using kinetics pre-trained models. But in our method, CNIP pre-training should be used with the other components that we propose here. So to conclude, we proposed attributes-aware network. It is a strategy to use CNIP for temporal action detection. AAN primarily comprises of a frozen CNIP encoder, along with these two new models, Attribute Extractor, which disentangles the nouns and verbs from the unified CNIP representation, and graph reasoning blocks to model the extracted attributes within the frame and across time. In future, we should rethink the use of CNIP for short-term video understanding. Thank you.